In this video, we're going to look at electromagnetic radiation. Recall that for an electromagnetic wave, we can describe that wave using three different variables. First, we can talk about the wavelength, or the distance between two peaks of that wave. Next, we can talk about the frequency, or how often that wave passes a given point in a second. Finally, we can talk about the energy of that wave, or the energy of a photon in that wave. There's two equations that govern the relationship between these three variables. First, we can talk about how wavelength is inversely proportional to frequency. We use the proportionality constant c, or the speed of light. Second, we can talk about how energy is directly proportional to frequency, and we use the proportionality constant, Planck's constant. Speed of light and Planck's constant. Now let's consider the problem down below. It says a given AM radio station broadcasts on 1610, that is 1610 kilohertz. Compare the wavelength, frequency, and energy of the signal from that AM station with the radiation from an X-ray machine in a typical dentist's office, which has a wavelength of 1 nanometer. So let's draw a line down the middle since we're going to be doing two different sets of calculations. For our AM radio station, we know that the frequency is 1610 kilohertz. I want to convert those kilohertz into hertz. There's 1,000 hertz per kilohertz, giving me a frequency of 1.61 times 10 to the 6th hertz. That's also equal to 1.61 times 10 to the 6th times per second. Now I want to pick my equation to relate frequency and wavelength, and say that the wavelength of an AM radio wave is equal to the speed of light divided by the frequency, where the wavelength equals the speed of light, 2.99 times 10 to the 8th meters per second, over the frequency, 1.61 times 10 to the 6th times per second. Looking at my units, seconds and seconds cancel, leaving me with just units of meters, which is good for a unit of wavelength. That equals the wavelength, and that equals 185.7 meters. Next, I want to calculate the energy of an AM radio wave. E equals hf, energy equals Planck's constant times the frequency. Here, energy equals Planck's constant, 6.63 times 10 to the minus 34 joules times seconds, times the frequency, 1.61 times 10 to the 6th times per second. Looking at just my units, seconds and seconds cancel, leaving me with a unit of joules, which is a good unit for energy. And that works out to 1.067 times 10 to the minus 27 joules, which makes sense because we have a very low energy electromagnetic wave here, and we're talking about a single photon, so it makes sense that it's a small amount of energy. Let's now compare this to my X-ray machine. Before we do any math, we see that the X-ray has a shorter wavelength. Knowing that wavelength and frequency are inversely proportional, if the wavelength of my X-ray machine is lower, I would expect the frequency to be higher. Likewise, knowing that the frequency of my X-ray machine is higher, I would expect the energy of that X-ray to be higher than the energy of AM radio. Let's see if we're right on this. Given a frequency, I want to first solve given the wavelength, I want to first solve for the frequency. So frequency is equal to the speed of light divided by the wavelength. For the X-ray machine, frequency, speed of light is the same, 2.99 times 10 to the 8th meters per second. And the wavelength here is 1 nanometer, which is equal to 1 times 10 to the minus 9 meters. That frequency works out to 2.99 times 10 to the 17th times per second, which again is equal to 2.99 times 10 to the 17th hertzes. Very, very high frequency. My next equation, E equals hf, energy equals Planck's constant, 6.63 times 10 to the minus 34 joules times seconds. And the frequency, 2.99 times 10 to the 17th times per second. Looking at my units, seconds and seconds cancel, leaving me with just joules. Makes sense. Energy is measured in joules. This is going to come out to 1.98 times 10 to the minus 16 joules. If we compare those two answers, I see a frequency that is much higher than it was with the AM radio. And I see an energy that, while it's still a small number, because we're still talking about photons, is significantly higher, is 10 orders of magnitude higher than the energy of AM radio. This tells us that an X-ray machine is going to give us much more dangerous radiation than AM radio will. The big take-home message is here. Wavelength and frequency, inversely proportional. Energy and frequency, directly proportional. C and H, speed of light and Planck's constant, are exactly that. They're constants. And the energy of a photon, while it's very, very small, if you're bombarded with lots of X-ray radiation, can be dangerous. Being bombarded with lots of AM radio, we're not so concerned with that.